right, why don't we get started? It's 2 minutes past 7, so I think it's nice to start on time for those who are here already. So everyone, welcome to the Computer Vision Meetup in July. I'm really happy that we were able to do this, even though we had to move it virtual. I was really hoping we could be in person, but as we all know, unfortunately, we can't be there. So just quickly before we get into the presentation, because it's been quite some time since we met, I just wanted to introduce the whole Anyline Meetup organization team. Myself, I'm Natasha, I'm the event manager at Anyline, and I'm also joined by Jan and Cesari as also part of the team. Hey guys.
Hi.
Hello.
Jan is a content writer and Cesari is a machine learning engineer here. So there's the whole spectrum, organization and promotion and engineering as well. So, and of course today we are having a guest speaker, which is Natalia Shepeleva, and she is going to be doing a wonderful talk for us today. Hi, Natalia.
Hi.
So was it now that you're going to sing the anthem for us?
Oh. Maybe. Maybe after, okay, as the closing note.
So quickly, the agenda, obviously right now we're doing the introductions and just saying hello. Natalia will give her presentation on the security and safety for a shared artificial intelligence project. And at the end, we will have a final Q&A, and then 8 o'clock or so, depending on how long the presentation goes, we'll have a closing. In terms of housekeeping, because this is virtual, we still want the ability for you guys to engage. So if you have any questions along the way, please raise your hand so Natalia and Cesari know that you have a question, and she can answer those questions for you along the way. So if everything is clear, I keep everyone, of course, on mute. Unless you have a question, please raise your hand. You can unmute yourself and then ask your question. So then with no further ado, I'm going to stop sharing my screen, and Natalia, I will hand it over to you.
First of all, thank you very much for inviting. Yeah, I feel a bit thrilled of giving presentations, especially yeah, just because it's always a bit of a nervous thing. And yeah, I think you have a really cool thing, and organizing this stuff, it's amazing for me. And like, I always like meetups because it's a nice environment. Very pity that I cannot see you all in person. So hopefully I might join one of their, hopefully you're gonna have an online meetups. Yeah, I mean online with the real visuals, with the real shaking hands and see you all face to face. And I hope I can visit that, or maybe you can, you know, come sometimes to SSH. So first of all, I'm Natalia, as Natasha already said. I'm a researcher at SSH for 3 years. And just recently, 1 year ago, I started my PhD in the Institute for Machine Learning at GKU. Both of these located in Linz. So my supervisor on one hand is Sepp Hochreiter from GKU, and on the other hand, Bernard Moser, maybe you know, our mathematician. He is our research coordinator. And today we'll just give you a small intro of what SSH is, which kind of projects we're doing, and then we'll more closely talk about security and safety for shared artificial intelligence. This is our recent full research project in which still we try to work a bit with the industry, and you will know why I mean still. So first of all, what is the SSH, where is it, and how to find it? So SSH is located in Software Park in Hagenberg. This spot, I hope you see it. We are particular at this building, having all 3 floors of this area. We're growing and growing. And right now, somewhere around this area, if I'm not mistaken, 2 new buildings are constructed. In one of them, we will soon finally move, and I hope then we will be able to invite you as the guests to us. Also, we have some spaces in the JKU, since we are kind of initiative of the Johannes Kepler University. There is an open innovation center lead, also recent building. We have some of the, just let's say open space tables there, and working for meeting our customers and our research partners. So SSH, or Software Competence Center Hagenberg, because it's in Hagenberg and Hagenberg is in Linz, close to Linz, is actually, regardless that it's named software, is a research organization or a research center, non-profit, and organized as the Commit Competence Center. I hope for someone it says something. Generally, we're doing a lot of research. We are, or the idea of our company, we still call it company, is to bring industry and research together. So we are not an outsource like a company, let's say like this. What we are really doing, we're having some partners in their industry, and for those who are willing to do some research and they don't have capability of their own, we provide this, let's say, solutions. The goal of that is, of course, to bring industry more closer to actual ground research in that done in the university. And on the other hand, we try to really use the university research and change it and being able to have it in the real case scenario, because quite often, maybe you know that research and the industry, they are going really apart in the separate ways. So we are supposed to be a bridge between that. We have different partners, as apparently colleagues of mine said, we have more than 100 partners. I don't know how it is much true. You have to ask them. And we have two main research areas. On one hand, this is a software science, and on the other hand is a data science. So I'm from the data science department, and more particular, I'm from the knowledge-based vision systems. So what are those two departments? This particular, gonna talk today about data science and about the projects that mostly we're doing there. So we have these two research focus. One is the data analysis systems. Here, our guys are working mostly with their time series data. We have 28 employees, several PhDs. We have different research projects outside of COMET. It basically means that we are actually doing some research which is not only supported by the Austrian government, but the additional one. And what is the goal of our guys is to take care about the data analysis and data management, trying to do prediction. Basically, this is a machine learning department, pure machine learning, which is working with data, which is analyzing all the types of data, and supporting companies with understanding which data thingy they have in there. So as the example, there is two projects. One is Smart Maintenance. It was done for BMW. It was for identifications of the critical irregularities and problems issues. If I'm not mistaken, they wrote a framework, and out of this work was written a paper, as you can see, by mostly of my colleagues. And this is one of the very important research outcomes we're really looking from all of the industrial projects. We would like to have research basis. We would like to have research, important research results, which are in most cases are actually papers. The second was monitoring and prediction of molding. Here, there was also a task to identify some patterns and have a prediction. Unfortunately, I cannot really tell you much about this particular project because it was done by my other colleagues. But if you're interested, feel free to write me mail and I will connect you to a person who was working in this project. And of course, we'll mostly talk about knowledge-based vision systems just because I'm from there. In this part, we are actually working mostly with their spatial temporal data, which is images, videos, tracklets. All our tasks are more or less connected to computer vision and deep learning. In fact, we are not that many, but yet we are quite powerful. We have several projects which are, let's say, are kind of valuable and bring in lots of money. Let's put it like that. Mostly we're working on tracking our bioinformatical imaging analysis and mostly industrial image processing. As for example, one of the projects was surveillance and prediction of the modeling, where we actually didn't have an images, but we had a tracklets, and out of this, we would need to create removing our misunderstanding or our noisy data. That's a bit different from our time series, because in fact, this data was already derived from their images. So basically we kind of lose some part of the image processing and then have to adapt our algorithms not on visual data, but on some representative data, and also had the paper on that. On other thing is more interesting, it's analysis of the quality inspection for the industry. In case, as you can see here, two different domains. In one, there is one type of the quality issue, things like a hole. On another one, another quality perturbations, which actually the customer would like to detect in different materials. And in this case, it's very interesting because a paper that was written by our colleague on transfer learning was actually applied to this industrial projects, and they have got quite good results. So as you can see, we're more or less working with the industries. And recently we got a project that calls Security and Safety for Shared Artificial Intelligence. And this is actually a pure research project. It was done within a COMET module. We had partners not only from Austria, which are RICAM and GKU, but also some partners are from Belgium, if I'm not mistaken, and Italy, Cagliari. Our goal is to bring three important domains, which are mathematics, deep learning, and security aspects. And all of these aspects, research aspects, should be within these groups working on and bringing our new methods and new model architectures. What is really interesting, especially taking into account SSH, is that first of all, it's an absolutely research project. So ground research, no company is required. On the other hand, we would like to still fulfill our mission, and we will have several company partners who will be interested in applying our research in actually their industrial cases. And by having them on the board, we will be able to know which kind of need the industry has at the moment, and basically they will steer a bit a wheel to show us where the research in these areas, which has not much investigated yet, how we can further push the research in the way that is beneficial both for the research community and for industrial community. So not like we did before, where there is an issue and problem and we try to resolve it with the things that we already have, or we find out some new research topic, but we try to simultaneously work on those two things together. So basically, what are the research aspects of this security, and why do we have so many shared security things? Basically, in case, if you have privacy preserving, deep transfer learning, deep learning, federated learning, any kind of a learning, different sources, different data. Then we train our model, let's say, on one machine, and we would like to use the same model on another machine, but our data was quite sensitive. So the goal of this research project in general is to make your network, your weights, your biases, first of all, secure. So in case if you transmit and transfer your information to someone, their privacy is still preserved. On the other hand, while you want to learn, you want to have you don't want your data being exposed during transform from, let's say, if it's in the cloud or even it's in your machine, you don't want someone to look at your data. So this is another way of preservation the data. So make the data being more secure, so not exposed again, but already on another setting, and being robust towards adversarial attacks. We have an ideas of how to do that, and for that we have our method for our geometrical understanding of the deep learning models here. I will talk about this a bit later. And that's why we want to bring the companies, because we see that this can be very useful for the different companies. If, for example, you have your medical institution, which had a training on identifying a cancer on the elderly people, and there is another medical institution who is doing exactly the same work, but they would like to have this identification in the young patients. Of course, we cannot share data. Of course, we cannot share networks at the current state as they are. But if we would use this privacy preservation, first of all, we could train the network such that it will be robust towards any kind of attacks. Second, it will preserve the information and security about every single patient during training. And while we transfer the model, it will be impossible to reconstruct the data from this model such that another institution will be able to use it and will be able to, and this model and this data in case of transfer learning will obviously help them to make this identification way better. We start this particular project in the beginning of 2020. Unfortunately, due to Corona, were quite apart and had to also have all our meetings online. On the other hand, we had a quite good research results, I have to say, with the team of ours at SSH and also with our partners. We already have 4 publications and we're quite happy about that. And we think that we're doing a good job in the progress of trying to fulfill our research goal. And right now, I will tell you a little bit more about our paper that we wrote together. The first one, Relu Code Space, together with all of my colleagues who are working in this SSH project. So what, Relu networks are simple things so far, and we want to investigate them and find out what is actually the geometry behind. And we start this by investigating a very, very simple ground-based thing, trying just to find out what's happening inside the networks. Because until we don't know what's happening inside networks, how do they work, why they work in this particular way, we unfortunately cannot move further in this privacy preservation and transfer learning. Because without clear understanding of basic things, it's nearly impossible to start speculating about something more complicated. So basically, the research should go from a very, very basic to more and more advanced things. So in maybe there is a special research direction called neural architecture search. They use and they try to find which kind of architectures are the better, which kind of hyperparameters you need to find for your particular data set, for your particular architecture, for your particular whatever else during the training, which optimizer, how to reduce the learning rate, what is the batch size, and so on and so forth. And they have certain quality indices, which you can see on the slides. And this is an impressive work of Christian. It was published just in 2019, in which he had 5 million models trained and evaluated only on Cypher 10. So if you just think about that, how many networks, especially look at the green bar, over here, greenish, yellowish, how many networks are actually similar between each of them in terms of quality that we used to look at, training time or accuracy or validation loss. And then comes obviously a question, which of all of these 5 million networks you actually need to pick up if you're, and okay, it's just a say for 10, but if you have your actual data set, how can you say which one of all of the networks you train generalize better if in fact your accuracy is nearly the same? That's kind of a big question, still kind of a big problem. We had our small example. I was training MNIST on VGG16. Yes, it's definitely over parameterized, but just as an example, are both training training hyperparameters were the same except learning rate. So batch size, training time, random seed, and so on and so forth were exactly the same machine, just learning rate differs. And as you can see, I have two accuracies, which are very similar to each other. They're both close to 1. And my question would be, which one of those two networks do I need to choose? Which one I will use as a production? Which one I would use, I don't know, and put it on my detection in front of my door and see if it's a thief or it's me. Which one is better? Unfortunately, we don't know. And unfortunately, no one knows. And this is a big issue. And we try to find out what happens inside of this network and what actually can we derive from it. Based on that, we have a theory of our polyhedral bodies of the ReLU networks. It was inspired by Montufar, and the idea was proposed by my supervisor and SSH coordinator, Bernard Moser, where we thought, perfect, we have our neural networks. Most of them are usually having our ReLU activations. So what's going next? Let's try to binarize this and try to go in the geometrical space of the network. So if we just look at the n-dimensional space, which creates by the neural networks during the training, how the weights and biases are aligned, it's really hard to find out what exactly form and shape it has. But if we just try to binarize it, maybe we could find what is there, and maybe then we can have or try to see the correlation between actually the input and the output. So it's going to be a bit of math, and please, if you have questions, either stop me or ask me afterwards. I will just very, very roughly to describe you what exactly is this. We first of all just defined a ReLU network, and then by defining this ReLU network, we say it's a function that maps input space M to the output space N. We have an activation vector A for any random input X, and every small k will be a layer, and we will have a multiplication of the ReLU and the linear function. So basically it's a ReLU, biases, and weights. After that, we can actually define a code for an input X as the binarized activation function. So basically, it will mean that if a ReLU activation says I've been activated, so we said, okay, great, any kind of value that is equal, bigger than 0 will be for us set to 1. Everything, if it's 0, then it's, well, 0. Based on this ReLU code, we can then have every layer of the ReLU as the code. And then in this kind of situation, we can compute a Hamming distance, because Hamming distance is simply a difference of our binary codes, so 0, 1s. And therefore, for each input, we will compute a Hamming, we will compute our code. And then for all of the inputs we had, we will compute our Hamming distance. So if we have Hamming distance, then we actually have a duality representation theorem of the ReLU codes, which basically says there is a 1-to-1 correspondence of the code space and the set of the equivalence classes. So equivalence classes for us is in fact just a tessellation, and tessellation is an intersection of this ReLU codes that we had. We just they're just so every ReLU code or ReLU code or ReLU activation is actually a hyperplane. So intersection of all these hyperplanes give us a cell. This cell we're going to call a tessellation. And because we will have this amount of finite number of the tessellation, simply because we have a finite number of ReLU activations, and therefore we'll have a finite number of all the possible codes, we can have a polyhedron. Then we can actually define the adjacency metrics in this tessellation space. So in our case, all the cell now will be represented just as their sequence of code. Yet we still don't know which shape it has, how does it look like, what is form of it. Maybe there is one tessellation or one cell in the inside of the another one. We don't know, but we have representation of each of these tessellation as the code. So if we look at the Hamming distance and we try to compare all the Hamming distances for all of the codes, in this case, we can say if our cells are adjacent between each other or not. So if adjacency is 0, then all the input belong to the same polyhedral cell. If it's 1, then all there are, so then the distance between two codes is 1, then actually those cells are adjacent to each other, so they're neighboring. And if it's 2 or higher than 2, then we actually don't know what's happening, so we just say they're distant. So they're distant, not adjacent. We don't know what is going there. They're just somewhere apart from each other. And this is actually our formulation of our code space isometry theorem, which basically says that there is adjacency between a metric and a ReLU space. So in theoretically or more clearly saying, we just find an equivalence or reformulate how does the input reflects to the actually output decisions. So maybe a bit more clearly will be from the experiments. So since we had a neural architecture search setup, it's quite strict to the random seeds, to the kernel and the biases setups, and to all the experimental setups. Therefore, it was one machine with a particular random seeds, with a particular biases, with a particular weights, and decided at the beginning. We had our defined setup as well, like as a batch size, loss, gradients, so on and so forth. A bit more is in the paper what exactly was there, and then we try to find define two architectures which we would like to observe a very big difference, and you will see what the difference will be. So in one case we have an autoencoder, and in another one we have a VGG. So for each of those, we had from 1 to 3 fully connected layers. So for autoencoder, it's a static 3 layers. For the VGG, we had derived from 1 to 2 and 3, and we tried to find out what is the difference between them. We didn't look at the output at all. For us, were more important, like output is the last layer when you say, okay, now if I have 10 classes, please tell me which one of those 10 is the image that I sent to detection. So we omit this part. We had only their fully connected layers in the architectures. And for those, we try to find what is the difference. But before that, if we come first, remember to this first experiments with 2 accuracies, this is a very, very strange effect and very interesting that we actually found out. So remember in this setup, we had a VGG with one of the data sets trained, and then for each of our class, as you can see here, 10 classes, we try, here should be 10 classes, we try to compute how many of these tessellations are there. So let's say if I have for one class, as you can see here, 4,000 samples, how many of the unique codes of these unique activations were there at every stage of the training? So at every epoch, how many of these tessellations per particular class I did observe? And with a big learning rate, as you can see, basically every single input belonged to each single cell. Theoretically, this is not what we were expecting, because ideally, let's say if you have an images between dogs and cats, which are we usually use, yes, in the experiments, if you have cats, you would think and you would assume that all of your cats should be very close because they share some certain features. So we would expect that for this case, our network would say, yes, I recognize that it's a cat, so I will then highlight exactly the same sequence of the relo activations. It's like, you know, in the brain, it's pink, 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 pink. Oh yeah, this looks like a square. So the same we would expect here. So if we have same class, we would like to have as less codes as possible. Ideally, there should be only number of codes should be equal to the number of actually classes. This is, of course, far from the reality with the current architectures, but this is what we would like to aim for. And as you can see, was not the case. Yet, on the other hand, for a bit bigger learning rate, we did not achieve exactly the same, but the number of codes are rapidly changed during the training, which still we don't know why and how. There is apparently a gradient updates somehow affecting this. There might be magnitudes, of course, but what exactly was the reason is still a question, and therefore we try to find out, like, okay, we see this evolution during the epochs. Okay, great, but does network actually do any kind of separation, or how does these codes are actually there inside? And therefore we tried to have two architectures. One is autoencoder and another one is VGG. So the goal of the autoencoder is to find similarities. So while all the classification networks are trying to find dissimilarities or trying to tell you very distinct different classes from each other, the goal of the autoencoder is to find as much similar as possible because it encodes the most sufficient and important information. And then from this encoding, try to reconstruct back the same your input only based on the most sufficient info. So if you look at these graphs, you would see that first of all, in the beginning, and this is FC0, that's the first row, there is kind of clearly separation. Unfortunately, the visualization tool, which called UMAP, is not the best. So unfortunately, we have to see that one class is overlaying over another one, but still they are distinct somehow. And if you look at the last one, it's quite hard to separate the classes. And this is happening not only for the one dataset, but for another dataset is exactly the same situation. So this gives us a kind of feeling that it's in fact encoding, that information is already constructed in this code space and then constructed in a such way that even though we lose some information about magnitude, it's still quite preserved. And it means that the network is indeed have some certain let's say understanding of what it preserves. So on the next experiments, that was with the VGG, In this case, of course, we would like to have as much separation as possible. So in one case, so on one hand, you will see a different learning rates again, which is, I would say, also a bit strange, that, and probably would say that the gradient is indeed differ a lot on how the clusters do construct. But what you would also see that a bit more we go down, this is our last layer, as more clearly the separation of the clusters is happening, especially for quite a big learning rate. And this is also a strange behavior, because usually what we do in the experiments or in actual production, yes, we try to use as small learning rate as possible, such that the network learns something, that the gradient descent doesn't fall very down, it step by step gradually tries to train something. And strangely, we see that a bigger gradient actually gives us a better separation, while it might not give the best accuracy. What to do next with this? There's probably many other things which I'm still trying now to investigate. I try to go a bit more in the graph direction and try to see how exactly are this code related to each other, because we would like to find the ways of using this, first of all, for identifying how and which networks are the best, and then trying to find a new metrics on how to make them more accurate and more robust towards adversarial attacks and towards the privacy. And in addition, to look if it's actually possible to use this sort of information, how to combine this information for their transfer learning, because adaptation of all these domains is quite hard. And maybe by understanding this particular domain, maybe by understanding what's happening in this n-dimensional data space, we will more understand how exactly the domains are aligned and how we can merge them together. That's it. Thank you. If you have questions, please feel free to ask.
Thanks so much, Natalia. Does anyone have any questions? We definitely have some time still left over. So if you have any questions, yeah, please, this is the time. Maybe we just leave your presentation up in case someone wants to go back for a minute. Okay, so I don't see anything in the chat at the moment.
Also, just in case, first things first, thanks Natalia. It was a very interesting presentation, very enlightening. Thank you very much. And we will also release a summary of today's computer vision meetup, including the slides of this presentation and the session recording tomorrow on anyline.com. So feel free to visit us, and we will also post a link to that and to all of that in our meetup group too. So yeah, that everyone is covered. But yeah, if there are any questions, just shoot ahead. Take the opportunity as long as Natalia is here to enlighten us.
Okay. Well, while we wait to see if anyone has a few extra questions, let me just go back to sharing my screen quickly. So the next point I'd like to make that about Meetup is that this is a community. So we would love to hear from you. You saw the whole organization team at the beginning of the presentation. Let us know, what do you want to hear? What kind of topics do you want to see? Do you want to present your thesis, your own personal projects? Or do you think your company would want to do a sponsor and talk about what they're doing? You know, let us know. This is definitely a community. We are not here to dictate all of the content. We'd love to hear from you. So feel free, if you have ideas now, feel free to let me know, or you can also send us an email or something through Meetup to let us know what you'd like to do. Our next meetup will probably be in September, and most likely it will be digital once again because we're not sure what's going to happen. So just keep that in mind. Probably in the next few weeks, we'll have something at least on the calendar so you can put it in yours.
Just a quick side note.
Sure.
We have a question right at the end, but still, from Hawan. And here's the question. Basically, what is the motivation why we have to choose two models on the basis of the learning rate? If you could answer this question, Natalia, this would be great.
Mm-hmm. So this was maybe not clear from my side. The point is not the basis on the learning rate, but the point is if you have similar setup with only one parameter changed, like in our case, it was learning rate, and both of your networks giving you exactly or close to the same accuracy or close to the same result that you would like to have, then your question is, which one of those two can you pick? Because the more global reason is which one of those two networks is better generalized, correct? So it's just our experiments where we had similar setup and learning rate was different. Maybe in your setup, you will have your networks will give you exactly the same values in case if you, for example, change only batch size. The point is that you simply need to find out the best network for your data in terms of generalization. And just by looking at the learning rate, training time, accuracy, training time, and loss, you cannot do this choice so far. I hope I answered it.
Thanks, Natalia. Let's see if there's any other questions. How do you define the best model?
That's a very good question. Usually the best model is obviously the one that should generalize better. But what do we mean by generalize better? Unfortunately, is yet not clear. At the current ways of how we train it and how I see it in the literature, and if you look carefully, most time we have a fight for the accuracy. We define that the best model is the one that gives us the best accuracy value for the validation or for test data. However, what could be really a pitfall that if for the test, let's say validation data, it gives you the best accuracy, it might not work as good as another model, which might have a bit lower accuracy, but its genericness is way better in your real case scenario. Did he? Yeah. Okay, great.
Now that we've had a couple questions out there, does anyone else have any questions? This is a great opportunity while we have Natalia. Here we go. How does the number of equivalent classes relate to how well model generalize?
Our theory so far is as less equivalence classes we have, as less cells we have with a correct classification, as better model will generalize. This is only the assumption. We cannot prove it so far. This assumption based on the idea that if we have, let's say one big cell with all our inputs in, then there is quite high probability that these points will have their mean will be small, or that they will be more or less in the center. If the point is in the center of the tessellation, then there is obviously a more space, let's say a distance to a borders of our of the borders. So there is more distance to the every of the ReLU hub space. And from this, we could assume that first of all, it given us a bigger space for generalization, and second, it might help us towards adversarial attacks. Did I answer it? Thank you.
Wonderful. Who's got the next question? We're a bit shy tonight, Natalia.
Me too.
Oh, we got one there.
Oh.
Notable, but first one first. But do you measure then the distance from the point to the polyhedra center?
No, this is, there is one paper, I can actually send it maybe a bit later, which are doing something like this towards adversarial attacks. They just measure distance from the point to the most closest hub space. We don't do this yet, because if I'm not mistaken, this part should be done not by our research group, by our partner research group. So I will need to ask them if they're doing this, because this is for them is the adversarial attack. As far as I know, some colleagues of mine are looking so far at the Wasserstein distance, but only in terms of regularization. So not really from the point to the polyhedra center, but more from the point to one of the polyhedra border. Because for us, it's more important how far it's from the border, because in this case, we could assume there's somewhere is a decision line, or either softmax or any other linear part. So it's not really, for us, doesn't matter if it's in center. For us, it's more important that it's simply as far as possible from the border.
Okay, we also have another question from Cesare. He said on the site of the project, he was reading that algebraic geometry is one of the mathematical concepts that you're using. Since algebraic geometry can also be very theoretical, how does it relate to your research?
Oh, good question, because I'm a bit more on the edge of technical and theoretical part. We have partners from RICAM, and they're actually looking more at their geometry and mathematics. So unfortunately, right now, I cannot really tell you what exactly and which kind of concepts we're gonna look there, because this is simply their part of the work. Particularly related to the ReLU, our idea is just to derive any kind of geometric knowledge about this n-dimensional space and utilize it. How exactly and which particular investigations our RICOM partners will do, unfortunately, I don't know. But if you're interested, feel free actually to contact my supervisor. He will gladly answer you. Thank you.
So let's just one last minute for any last minute questions. Well, Natalia, it was really great to have you with us. It was great for you to give that presentation. It was good to have you here, and hopefully we get to see you sometime in real life when we have a meetup back in our offices. That would be great.
Thank you very much for invitation. I really like it. I would gladly try to convince some of my colleagues to give other talks because we have really a lot of things and projects. I hope we can actually meet, yeah, in reality, and maybe I will ask if it's possible to have a Anyline outside at SSH at some moment, you know, guest talks.
That would be
It'll be
great.
great to have you.
That would be fantastic. So I guess then that's it for the evening. We're really happy for everyone who joined us. Hopefully you enjoyed it as well. Please let us know what you'd like to see next time. Please offer to also give a presentation. We'd love to see what you guys are working on. So please reach out via email or via Meetup. I'm happy to take any of those suggestions. Otherwise, I wish you all a really great evening, and we hope to see you the next time. Thanks, everyone.
Thank you very much.
Thank you.
Bye-bye.
Bye.
Bye.